fellow mathematicians. Welcome to the podcast where math is figure-outable. I'm Pam.
And I'm Kim.
And we're here to suggest that mathematizing is not about mimicking or rote memorizing, but it's about thinking and reasoning, about creating and using mental relationships. That math class can be less like it was for so many of us and more like mathematicians working together. We answer the question, if not algorithms, then what?
In today's episode, we're going to dive into the world of multiplication and talk about a particularly useful strategy, and one that I probably use the most often until I cemented a variety of others.
So let's make one thing clear. Sometimes people hear us talk about strategies, like today we're going to talk about a multiplication strategy, and they think, yeah, it's like this vast, unknowable list of strategies. There's like so many of them out there that, like I'm sure I could pick up one or two of them, but it's not really important because it's just, like this huge universe of strategy. That's not actually true. There's really just a few important ones.
Right.
And today we're going to focus on one of those important multiplication strategies.
Yeah, and because we feel so strongly about developing relationships first and then naming it, we're going to actually name this strategy in a bit.
Yep. So before we get into it, what do you think people do when they do mental math? When I say the words mental math, what comes to your minds? Now, Kim's chuckling a little bit because we've had this conversation before. Mental math, lots of people hear that phrase, mental math, and they think to themselves, that's when you do it all in your head. That's when you've got all the stuff sort of happening in your head. And that might be true, but we're going to quote Kathy Fosno again, who said, mental math does not mean that you do it all in your head. Mental math means that you do it with your head.
So good.
So do you think, great quote from Kathy. Do you think that when we say mental math that you see somebody, they're doing you can kind of see their eyes kind of go up and they're thinking or whatever. Do you think they're doing the traditional algorithm in their head to solve that problem? So like somebody said, hey, here's a multiplication problem. Somebody says, oh, I'm going to do mental math. Whether they write something down or they do it in their head, you see them sort of like thinking and you think that they are doing the steps, like they've got the single digit and they carry the one and then they have the magic zero or like whatever the steps are in the algorithm. That's what they're doing in their head. Guess what? They're not. For the most part, if anybody's doing mental math, they're able to successfully compute in their heads. They're actually not doing all those steps. They're not mimicking steps of the algorithm at all. And what's kind of embarrassing is, maybe you never thought that. That's fine. But even if you didn't, if I may suggest to you, many of us did. So I assumed that when people were doing mental math, they were just doing the algorithm in their head. I knew that the definition of addition was that traditional algorithm, or the thing that you do when you multiply was that traditional algorithm. And so what else would people be doing in their heads? Like they've got to be doing all those steps and cross the outies and carry the one, the magic zero, like whatever it is, they were doing that. And I couldn't do that. I could not keep track of all those steps in my head. I had to write down those steps in order to keep track of all of them. And so I just, I looked at people that did mental math and I was like, well, I don't know why you can keep all those little steps and cross the outies and zeros and stuff, but whatever, that's not important because I can do it on paper and I'm totally okay with that.
Yeah, I have heard you say that before. And I got to be honest, I didn't really believe that that's what you actually thought. But we had this experience lately, right? And I got to see it firsthand. So we were taking video of kids for a project and asked our—
Serves you right, by the way, for not believing me.
And we asked our camera person to ask a variety of kids some questions. And one of the questions was 99 times something. And I was watching the video later and we talked, right? I called you because I was so surprised that a few of the kids were actually doing what you thought mental math was. They literally heard the problem, put their finger in the air wrote the problem, like if it was 99 times 37, drew the line, and then started doing the steps that they had been taught to do. That actually happened on video. And some of the kids got further into their steps than others, but every single one of them at some point looked at the camera and said, I just can't. And I, in that moment, watching the video, really felt for them
right.
to think that they thought that some people were just holding on to that. I feel like I would feel inferior if I thought that was the thing to do and that some could do it and I couldn't.
Yeah, I mean, so deep down, I did. I wondered
Yeah.
why people could kind of hang on to all that stuff, and I sort of dismissed it. I kind of did this with a lot of things I wasn't good at. You're like, well, if I'm not good at it, then it must not be worth doing. That was like sort of my immature way of kind of handling not being able to do stuff. And so it was interesting for you to see that there were other kids in the world
Sure.
who thought like I did, that's sort of what was happening in kids' heads. And so they tried. The camera person said, "Hey, would you do this problem?" And they're like, "Oh, I guess I'm supposed to, and you're not letting me write stuff down. So let me see what I can, let me try, see if I can do it." And no, I just can't. And like you said, our hearts just sort of go out to these
Mhm.
kids because could we share something fun? Maybe you've played with numbers. Maybe you've used relationships. Listeners, you're hearing me say this, and you're like, "Pam, that's really like lame that you thought that." So maybe you didn't think that way. Maybe you're the one that could kind of do some stuff in your heads. What's interesting is we think that we can purposefully help people build those relationships that lend to strategies. That stuff that you were sort of naturally doing in your heads for whatever reason, we can purposefully help people do that. We don't
Mhm.
have to leave me and these poor kids out in the rain thinking, "Oh, I guess, like because I can't hang on to all that stuff, I can't do mental math." No, we can actually give people the idea, "Hey, this is a thing. It's a thing to use relationships, not all those memorized steps that you're mimicking. Not that. It's about using relationships." And once we let people know that that's a thing, then they have access to it. That's what mathematicians do. Before in the podcast, we've quoted the research study by Ann Dowker, who went to a bunch of mathematicians and said, "Hey, mathematicians, we solve these problems," and gave them a bunch of arithmetic problems. Said, "If you'll please solve those problems, I'll just sort of watch you. If you don't mind, I'll just kind of interview you about what you do to solve those problems." And out of all of the times that those mathematicians solved those problems, how much of the time do you think those mathematicians were doing what I thought, that they were repeating steps of the algorithm? Like half the time, like 90% of the time? How about 4% of the time?
Mhm.
Like almost none. Like almost never were they repeating those steps to solve problems. So what in the world were they doing the rest of the time? Well, they were doing what Kim does naturally, and now what I can do, and what we can all do if we know it's a thing. We can use the relationships among the numbers to solve those problems. So, Kim, today's episode, let's get down to talking about one of those major relationships for multiplication. Go.
Yeah. So actually, in an earlier episode, we talked about using 100 times anything or 100 times something to think about 99 times anything. And in the video that I talked about earlier, I just wanted to share with you that we caught a dad in the background who piped in and was talking to his daughter when she got done being interviewed. And she said, "Hey, Lexi, 99
Wait,
is."
wait. He said, right?
Yeah,
You said, she said.
oh, I'm sorry. He said to his daughter who had been interviewed,
Right.
"Lexi, 99 is so close to 100, and you could have rounded up one and found 100 times 37 to get 3,700 and then subtracted that 37." And she lit up and she said, "Oh, yeah, that would have been so much easier." She just
Isn't that
didn't know it was
interesting?
a thing. Yeah.
Oh, it's so interesting that we hear about a bright young lady, right? I mean,
Yeah.
she's precocious, she's cute, she's on the video, we're taking the video and the whole thing, but had never thought about that kind of relationship.
Yeah.
And then also interesting, dad listening in the back is kind of like, "Hey, could you kind of think about it this way?" And
Mhm.
oh, like just letting her know that that's a thing. Instantly, she was already sort of able to hang on to the idea that that could be a thing.
Yeah.
So, Kim, how can we build that in kids, or I mean, really in adults, right? Because I
Right.
came to it later in life. I was definitely an adult when I learned how to do it. We like to use the instructional routine called problem strings. We don't think it's enough to just do a problem here or there to talk about our strategies. Although we do that sometimes on the podcast just to kind of give you a glimpse of what's happening.
Mhm.
We really like to use strings of problems that are purposefully written in a certain order in order to help students develop relationships. It's all about development and progressively help students think more and more sophisticatedly. So,
Mhm.
y'all, we love to do some math together. So this is going to be one of those times where if you're driving, go ahead and hang with us as much as you can in the air. You might want to re-listen to this part with a pen and paper later, if you want to. So don't no dangerous driving at this point, but we are going to do a little bit of math. All right. So are you ready, Kim? I'm going to give you the problems. I'm going to ask you to solve them and explain your thinking if needed. All
Okay.
right. So
Okay.
first problem of the string. Here we go. What is 8 times 7?
Okay, that one is most missed fact, but I know it. It is 56.
All right, so you might use a relationship, you might just have it at your fingertips. Either way, we want you to be able to, retrieve it fairly readily. We call that automaticity, but either way, you've sort of got 8 times 7 is 56. The next problem in the string, what is 80 times 7?
Okay, so that's just 10 times more. 80 is 10 times more than 8. So that's going to be, the answer is 10 times more. So that's going to be 560.
So you're thinking about 10 times, and there's this lovely 10 times thing in
Yep.
our number system. So if 8 times 7 is 56, then you can think about 80 times 7 as 560. Cool.
Yeah.
Next problem. What is, let's see, let me just review that. You just said 87s was 560.
Right.
87s was 560. Next problem is 79 times 7.
Oh, that was really helpful that you said 87s because now I'm thinking 79 sevens. That's just going to be 1 7 less than my total, my product. So that's going to
Mhm.
be 560 minus 7 is 553.
Sure enough. Cool. Good thinking out loud. All right. So if we could, you've just sort of used some problems to help you think about kind of a crankier problem, right? Like
Mhm.
79 times 7, you could have done a couple different ways, but one way that you can do it is to think about 87s to help you think about 79 sevens. Cool. All right. Next problem. Ready?
Yep.
I'm going to give you another most missed fact.
Okay.
8 times 6.
48.
All right. So if 8 times 6 is 48, then what's 8 times 60?
480.
Because you just sort of scale it by 10, right? 8
Right?
times 6
Mhm.
is 80, so 8 times 60 is 480. Cool. Anybody want to guess what the next problem is? If 8 times 60, if I've got 68s is 48, then what's 8 times 59?
8 times 60 was 480. That was 68s, and I want 59 eights. So that's just 1 8 less. So 472.
Because 68s was 480 and
Yep.
1 less 8 gave you 472.
Right.
Nicely done. Very cool. And then at this point in the problem string, so we've just given you sort of some helper problems to help you with the clunker. I gave you 8 times 7, 80 times 7 to get 79 sevens. Then I gave you 8 times 6, 8 times 60 to get 8 times 59. Then I might say to students, hey, so if you were sort of staying in the same vein, kind of the same pattern that we were just doing, what if I gave you a problem without the helpers? Could
Mhm.
you come up with the helpers that would be kind of in the same pattern that we just used to help you find the answer to a problem like 6 times 49?
Okay, so 6 times 49 is really close to 6 times 50 or
Hmm.
56s. And I know 56s is 300. So I need 49 sixes, which is just 1 6 less. So 294.
And how did you know that 6 times 50 was 300?
Because I know 6 times 5 is 30. So 10 times bigger is 300.
10 times 30 is 300.
Right.
And then since we don't need 56s, you only need 49 sixes, just one less 6.
Mhm.
Nice. Nice. It's excellent thinking. What
Thank
do you
you.
think, listeners? Like, this is a way of helping you and helping students kind of think about using a particular relationship. Now, that's not the only way that Kim could have multiplied 6 times 49,
Right.
but we kind of had our brain, or hopefully we had everybody's brain sort of thinking about, ooh, this kind of pattern that we were using. And so, what's it close to? A little bit too much. Oh, so I could think about a little too much, 6 times 50 to help me think about just a little bit under that, 6 times 49, or 56s to help me think about 49 sixes. And that's a problem string, a string or series of problems in order to help learners develop relationships. And like I said, that's not the only relationship that she could have used for 6 times 49. Kim, what's another relationship that you could have used for 6 times 49? Let's test Kim just a
Yeah,
bit here.
I could have split by place value a little bit. I could have said 6 times 40 and then 6 times 9 and added those two
Nice.
together.
So it's not like we want that strategy to go away.
Right, right,
It's just that we want students to own both strategies. We want them to be able to look at both relationships and then choose in the moment which one do you want to use. And one other just sort of tidbit we'll throw in here. Do you know that the mathematicians not only use alternative strategies, but they often will play between the two of them.
right.
So they'll often think about a problem like 6 times 49. I'm sharing this today because I didn't know this, right? So it's important for us to share this message that Kim might have thought about. Well, let's see, I could do 6 times 40, or I could do and add 6 times 9, Or I can think about 6 times 50 because I know 6 times 5 and then just take away a 6. Like she has both of those strategies in her repertoire. And so now she has the power to choose. That's empowerment. Empowerment is when you own both of them and you can choose. If you just only ever learn one strategy and that's the only thing you can do,
Mm-hmm.
that's not power.
Right.
That's just being stuck, pigeonholed into having only one and only one strategy. So generally, after we've done some problem strings with students, we might have done one problem string to sort of introduce the idea. We might do another one to kind of up the ante and get more students thinking about it. And by the time we kind of have most students in the class sort of playing with this strategy, then we kind of cement the learning. So let's do that here. Ideally, we would have done 2 or 3 more problem strings with everybody,
Right.
listening so that you'd really get it down. We're on a podcast, it's not going to quite work so well. So let's go ahead and cement the learning. What we would do after we get most students sort of playing around with that strategy, with those relationships. So Kim, what's sort of going on here? How would you kind of generalize what's happening as you thought about 6 times 49?
So I think the simplest way that I would describe that is that we want to make one of the numbers nice. It's kind of close to
Mm-hmm.
a nice number, and then we can multiply like 6 times 50, that nice number, and then subtract the extra, right?
Yeah. Okay. Cool. So this nice number idea, friendly number, landmark number.
Hmm.
Like if you're thinking about 6 times 49, you might go, "Ooh, not a nice number." Oh, but actually, it's nice because it's so close to an even nicer number, right? It's so close to 50. It's so close to a landmark or friendly number. And if you can find that multiplication, then like you said, subtract the extra.
Hmm.
Cool. So we would want to have that conversation, kind of generalize that's what's going on. Okay, so if that's a set of relationships, what are some things we could do with that?
You ready to do some math?
Yep, I'm
Okay.
ready.
So we were just talking about 49. So what if we said, what's 49 times anything? Like, what if I asked you 49 times 24? How would you think about that one?
Okay, 49 times 24.
Yep.
So let's see. I don't think I know 50 times 24, but I think I could figure it out easier than I can figure out 49 times 24
Hmm.
because I know that 50 is half of 100. So I can think about 124s. That's 2400. And if I know 124s is 2400, then 50 24s is going to be half that. And half of 2400 is not too hard. That's just 1200. And so I'm just keeping track of what we're doing. And I got to tell you, I just got an adjustable desk and I didn't click the lock on my adjustable desk. And so as I wrote down 1200, my desk went up. It's okay, sorry. Just a little random podcast humor there. Okay, I'm going to lock my desk. So it's going to stop doing that. All right, what were we doing? We are doing 49 24s, and I found 50 24s by finding by finding 100 24s and then finding half of that. So that's 1200. So 50 24s is 1200, but we only want 49 24s. So now I have to think about 1200 minus 24. If you've listened to the podcast, you've
Hmm.
played I Have You Need with us before. So if I have 24, what's the partner to 100? Is that 76?
Yep.
So 1200 minus 24 is 1176, 1176. Yeah. Right?
Yep.
How'd I do?
Nicely done. Nicely done.
Totally cool. So let me just put one. I kind of told on the whole adjustable desk raising thing because I wanted to make sure that you know that I'm pretty sure Kim, when I gave you that problem string, I think you did that in your head because you just sort of hold
Sure.
things in your
Yeah.
head a little bit easier than I do. And I wrote down 49 times 24, and then under that I wrote 50 times 24, and then under that I wrote 100 times 24, and then wrote equals 2400.
Yeah.
Then I found the 50 times 24. So I went back up to where I'd written 50 times 24 and wrote 1200. And then I went back up to where I wrote 49 times 24 and I wrote 1200 minus 24, thought about I Have You Need, and wrote 11676. So it's okay. I want to just give the audience permission
Yes.
to keep track of your mental thinking, that that can be a thing. I am not less than because I don't hold all that in my head. Maybe that's something someday that I'll get better at. I think I have gotten a little bit better at it, but that's actually not my goal. My
Right.
goal isn't to be able to hold things more in my head. My goal is to be able to use relationships to solve problems, to mathematize. And we're here to suggest that that doesn't necessarily mean that you can just do it all in your head. If you need to keep track, that's totally okay because I do.
Yeah.
Even
Well, and
though,
it's funny because when you call or when we're talking, I often have a pencil in my hand. I'm a pencil, not a pen
mm-hmm.
girl, but I often have a pencil in my hand because when we're in the midst of stuff, I want to keep track as well. So it's not about, that I never write anything down either.
Yeah, and you tinker. Like if we were to look at
Yes.
your paper, you just sort of write down what you need, right?
Right.
It's not like a formal argument. It's not something that you could turn in or that somebody could necessarily follow your thinking. Because in the moment when you're just tinkering and playing, that's not necessary. You're
Hmm.
just tinkering and playing.
Yep.
Y'all, that's mathematizing. Mathematicians tinker and play, and how much fun is that? All right, so I did some math. Kim, back at you. You ready?
Yep.
Okay, how would you solve a problem like 18 times 13?
18 times 13. So I like 18 because it's really close to 20. So instead of 18 13s, I'm going to go with 20 13s.
Okay.
And I know 20 13s because I know two 13s. Two 13s is 26. So 20 13s is 10 times bigger. That's 260. So I'm actually going to write that down. 20 times 13 is 260. And then I have too many 13s. In fact, I have too many 13s. So I'm going to subtract 2 times 13, which is 26. And again, because I'm familiar with partners pretty well, I'm going to say 260 minus 26 is 234.
Yeah. And I had to think about that. Nice.
Yeah.
So you had too many 13s,
Uh-huh.
and so you got rid of those 13s, and two of those 13s are 26,
Yep.
and that's how you solve the 18 times 13. Nice.
Yeah. Okay, you want can I give you one with decimals?
Sure.
Okay.
Go for it.
Here we go. How would
Okay.
how would you find
I have my pen, not pencil ready.
Okay.
Go.
Do you normally write with a pen?
I do.
Oh, okay. How would you solve
Oh, okay. No judgment there. No judgment.
I need
No
my
judgment in
trusty
that tone.
Ticonderoga. How
I know.
would
I
you
mean, if I'm going to write with a pencil, it's a Ticonderoga, but
Okay.
for the most part, go, go,
All
go.
right. 3 and 9/10 or 3.9 times
Okay.
2 and 2/10. Yeesh.
Okay, 3.9 times 2.2.
Yep.
Yeah?
Yep.
Okay. So I'm going to think about not 3 and 9/10, 3.9 times 2.2. I'm going to think about 4 times 2.2.
Okay.
And that's not too bad because 4 times 2 is 8. And so 4 times 0.2 is 0.8. And so 4 times 2.2 is 8.8 or
Yep.
8 and 8/10. So that's 4 2.2s, but I only need 3.9 2.2s. So I need a tenth less 2.2s. So a tenth of 2 and 2/10, or a tenth of 2.2, which is like dividing by 10, that's 0.22 or 22 cents.
Oh, I'm glad you said
So
money. Yeah.
yeah, so far I've kind of got 4 times $2.20 is $8.80 minus a tenth, which was 22 cents. So I've got
Mhm.
$8.80 minus 22 cents. And so I'm going to think about that as I'm actually going to think using constant difference. So I'm going to think about that as 8 cents more. So that's like $8.88 minus 30 cents because I had $8.80 minus 22
Yep.
cents. So now I've got $8.88 minus 30 cents. And that is $8.58.
Nice.
Yeah. Woo! Decimal multiplication, thinking and reasoning using relationships. So why the over strategy? What like makes it bam such a cool strategy?
Well, sometimes you're given a problem that doesn't really look all that great, right? Like
Mm-hmm.
3.9 times 2.2 and 18 times 13 do not look so friendly, but
Mm-hmm.
it could be really close to something nice, something landmark.
Yep.
And the more comfortable that we are with those landmarks, the better we can be at doing stuff that's like a little bit over or a little bit under, right?
So strategies are not one size fits all.
Right.
We use them when the numbers make sense to use that relationship. And the over strategy is just so cool. So, to wrap up, next time you find a multiplication problem, look to see if the over strategy might be a good one to use. When you find one, tweet it out with the hashtag #MathIsFigureOutable.
Hey, and remember to join us on Math Strat Chat on Facebook, Twitter, or Instagram on Wednesday evenings where we explore problems with the world. Many problems for which the over strategy is a great one to try.
Absolutely. And we've created Math Strat Chat Central, where you can find all the problems ever created and have lots at your fingertips. Click on one of the problems and it'll totally throw you into the Twitter feed where you can see all the strategies shared from around the world. So, if you're interested to learn more math and you want to help yourself and students develop as mathematicians, then don't miss the Math is Figure Outable podcast, because math is figure outable.